All right, looks like we are live, and I want to welcome everybody to Standing for Truth. My name is Donnie, and I am your host and moderator for tonight's great geocentrism debate. Specifically, we are debating the proposition geocentrism is not a possible or even scientific explanation of the universe, with Jackson Roe taking the affirmative tonight. I am thrilled to have Dr. Robert Sungenis and Jackson here to debate this important topic. And so, gentlemen, why don't we break the ice? I am excited for this debate. I know the audience is as well. They've been camping out all day waiting for this epic exchange. So, Robert, why don't we start with you? Been a couple months or so since you've been here. Your last debate was on the same topic, and it was a debate to remember on geocentrism. So, Robert, how have you been? And a little bit about yourself.
Okay, well, I've been since that time, 2 months ago, wasn't it? I've been okay, still breathing and able to get up out of bed in the morning. So if that happens, I'm good.
That's all we can ask for.
So let me see. I got started in this topic, 23, that would be 30 years ago. So I'm no spring chicken, that's for sure. But one Sunday afternoon, I was at my computer. I had nothing to do, except I was going to go play basketball later on that afternoon. And I was at my computer just fishing around the internet, and I came across this PhD in astronomy talking about the Earth being in the center of the universe and not moving. And I said, what is this? I've never run across that before in my life. And so I had to make a decision that day. Either I'm going to press the next key on my keyboard, or I'm going to go out and play basketball. So I decided to press the key and got into his website and started reading it. And I was a physics major in college for a couple of years, and then I dropped it and got into theology and religion. But I knew enough of the physics to read and understand what he was saying. And I said, okay, that makes sense. That makes sense. That makes sense. And before you know it, I was totally engrossed. And one of the reasons why I became engrossed is because the Catholic Church in Galileo had a big bout, as you know, 400 and some odd years ago. And the church said that it was a heresy to believe in the heliocentric view. And they actually condemned Galileo, not many people know this, as a suspect heretic of that very theory. And I'm a Catholic, and I've been that way for the last 30 years. It's amazing. 30 years, each of them. Okay, so I just discovered that. And I said, okay, well, if the church has been right about everything else, as a Catholic, then they should be right about this. And so I'm going to go in there whole hog, and I'm going to see if it's right. The more I dug, the more convinced I became that indeed they were right and Galileo was wrong. As a matter of fact, my first book on this has the title, Galileo Was Wrong, the Church Was Right. And that was 30 years ago or so. And so that's what started me off. And here I am today, still debating the topic, and I'm glad to do so. So that's my background.
One thing I appreciate about your books, Robert, among many things, is the titles of your books. They're catchy. Like your Flat Earth one. What's the name of your Flat Earth book?
Flat Earth, Flat Wrong.
Right. Tell us how you really feel about the Flat Earth.
Yeah. And a lot of people suggest to me, they go, why don't you tone down that title a little bit, And I go, no, man, hey, if I'm convinced of it, right, I'm going to tell you right at the beginning,
Right, exactly. You're not hiding anything.
No.
You want your audience to know exactly what you think about this position. So you've given up a career in the NBA being the next Michael Jordan. And I appreciate it because I enjoy these debates, Robert. So I'm glad you chose to look into that topic rather than go play basketball that day.
Hey, nobody's ever said that to me, Donnie. So I really appreciate that.
Hey, the least I can do. Okay, Dr. Sungenis, I appreciate the introduction. For those in the audience that want to see more from Robert Sungenis, firstly, you can find him here on the channel, I think, about 5 times or so on a variety of debates and topics. Also in the description box, I have his YouTube channel and website linked for people to check out. Okay, Jackson Roe, good to have you back as well. It's been about a couple months as well, I think. Your last debate was Dr. Dino himself, and that was a lot of fun. So,
yeah, I think it was. Yeah.
How have you been? And
Been
for the
doing
audience,
good.
a little bit about yourself.
Yeah, I've just been doing some science-related stuff like I do here and there, and biology stuff like that. But I've been preparing for this quite a bit. It's been taking up all my research time, basically. Probably watched The Principle, Robert Sungenis' movie on this subject probably 3 times at least, just going over it and a bunch of his other stuff to prepare. So hopefully I'm prepared for it. We'll see how it pans out, but I've been excited for this debate. So, I mean, that's really it. I'm excited.
Yes, word is you haven't slept at all in 2 months since we set this debate. You've just been preparing 24/7, no sleep, lots of Red Bull and coffee. And so, okay, this is going to be an excellent debate. We've already got a fantastic audience, a lot of people expressing how it's good to see so many people engaged and interested in this topic and other science related topics. You know, these are important. And we got 2 great guests to engage it tonight. So let me go over the format for tonight. It is going to be more formal, as we want to have a scientific, a scholarly discussion here tonight on the proposition. So we're going to have 12-minute opening statements. Again, Jackson Roe is in the affirmative, and so he will begin with his 12-minute opening. What I can do, gentlemen, is give you a 1-minute warning at the 11-minute mark, and that way you'll know to start winding things down. Then we're going to have 2 rebuttals. Rebuttal 1, it'll be uninterrupted, 8 minutes. Rebuttal 2, uninterrupted, 5 minutes. Then we'll have a little bit of an open discussion where you both can ask each other some questions and discuss each other's points. Then we'll have a 5-minute closing statement. Robert, Jackson, you can wrap up your thoughts and points for that. And then we'll get you guys in the audience involved. We'll have a little bit of an audience Q&A. Again, the topic geocentrism. So please, if you have a question, make sure it's on topic. And let me know who the question's for, Robert or Jackson. And then tag me either at Standing for Truth or at Donnie. And that way I won't miss your question. Okay, with that, we're going to get right into the first opening statement for tonight. Jackson Roe, whenever you're ready. Please let me know.
Let me share my screen. Hang on a second. Always takes me a minute to figure out how to do this again.
If you need help, let me know. I'll get the timer.
All right, it should be sharing. Just let me know when you see it.
Yes.
You're okay. Good. All right, I'll jump right in, starting now.
Okay.
All right, the Jupiter-centric universe. In this model, it has all the same physics of the geocentric and the heliocentric. I think Robert simply chooses to place the Earth in the center because of the Bible, but you can do this with any reference point, really. And I'm kind of jumping right into some technical stuff. The audience may or may not know what I'm talking about, but Robert will, so it'll clarify as the debate goes on. This ether experiment, I used a laser reflected off of a concave mirror to produce these interference fringes, they're called. I did this experiment outdoors and indoors, night and day, and tested in an underground concrete tunnel at a local college. And there were never any changes in these fringes. And it's predicted that they would change in certain conditions based on certain models of ether, depending on what you subscribe to. So ether is therefore either imperceptible or it doesn't exist. And the Michelson-Morley experiment has been talked about a lot. I kind of skipped that, went to the Kennedy-Thorndike experiment, which is really an expansion on the Michelson-Morley. It uses 2 mirrors like the Michelson-Morley. However, the mirrors are different distances from the light source. This experiment proves length contraction and that no preferred reference point are factors, which confirms relativity and disproves ether. And I'll just kind of skip this slide for now. It's kind of too much. In the principle, it was stated that if the Michelson-Morley experiment were done on the moon, for example, relativity would collapse. Interestingly, using lunar retroreflectors placed by the Apollo missions, the Kennedy-Thorndike experiment was tested, and relativity didn't fall apart, but was confirmed, and the concept of ether didn't hold up. Another experiment, piece of the puzzle, the Ives-Stilwell experiment, confirmed time dilation. The first confirmation of time dilation in an experiment. And in Robert's model, a Foucault's pendulum should work on the equator some of the year because the sun's orbit has to be kind of irregular or not perfectly aligned with the equator to account for the seasons on a static Earth. However, Foucault's pendulum won't ever rotate on the equator because it's always perpendicular to the axis of rotation. And this is my foot actually on the equator in Ecuador in 2012. That's my dad right there, standing between the northern and southern hemispheres. And that's the big monument. In all observations in the universe, objects with less mass orbit objects with more mass. To say the Earth is a singular outlier is an extreme case of special pleading, in my opinion. This is just talking about how global positioning systems rely on relativity, which I believe Robert has some problems with some aspects of relativity. Geostationary orbits are used by these global positioning satellites, which would only be a thing if the Earth was in fact rotating. GLONASS, which is the Russian system, has 24 satellites. GPS, the American, has 32 satellites. Here's a GPS constellation in their geostationary orbits, just kind of an illustration. And to deny the Earth's rotation denies that these work. For example, the Excalibur GPS artillery shell or this 2003 GLONASS receiver of the Russian military. The Hafele-Keating experiment, which confirms relativity. Atomic clocks brought on airplanes went west and east. They were compared to atomic clocks left on Earth. Not only does this prove time dilation, but the eastward rotation of the Earth as the clocks were left on Earth and not in space. The Chandler wobble is the rotation of Earth's axial tilt separate from its daily rotation. The Chandler wobble takes 430 some odd days to complete a cycle. Ether, or the universe moving around the Earth, can't account for both the daily rotation and the Chandler wobble. It would have to account for one or the other. So this doesn't make any sense in Robert's model. The Earth's core is a giant dynamo magnet. If it wasn't rotating along with the rest of the Earth, we would have no magnetic field. We would all die pretty quickly from cosmic rays or solar radiation. And gravity assists use the force of gravity of planets to accelerate space probes to their destinations. Robert acknowledges that the WMAP and Planck are real, those space probes. So is Cassini real? It relied on heliocentric data and confirmed all of it with its massive magnetometer right here. And same for Juno and many other probes, like a lot of probes do these gravity assists. Juno flew by Earth when the Earth was located at a different position. Again, this data is proven by its magnetometer. And basically, this is either not real or it really went to Jupiter. So here's this has been talked about before, but here's a 4-hour time lapse of stars moving across the sky. So I did some math. I may or may not be correct, but it illustrates the point, even if I'm wrong a little bit. 1 billion light years away, that would be 9.75 trillion miles per hour. So that's 16,250 times the speed of light for a 1 billion light year away star if it's moving around the Earth. So 13 billion light years or so maximum. The furthest stars are moving 200,000 times the speed of light, at least. I might be wrong on that. I think it would be higher if I'm wrong. And luno-retroreflectors placed by Apollo take into account Earth's rotations for measurement. I actually contacted one of the scientists who works on this, or used to, Thomas Murphy. He said, quote, "I am no longer personally doing so, but others in the world certainly still do use the reflectors. They're precisely where they are supposed to be, exactly the size they are said to be, and oriented just as they should be." And I'll skip that slide. And Roberts made statements doubting black holes, I believe. So either black holes are real or this image isn't. It was obtained by radio telescope interferometers. So this was either a faked image or it's really a black hole. How much time do I have left, Donnie?
Good question. You have, let's double check. You just hit the 6.5 minute mark. So you got a little less than 6 minutes.
Okay. These 4 points of light are the same quasar been around a lensing galaxy in the foreground here. Its gravity bends the light. This would only be possible if what we understand about relativity and gravity are true. And this is another lens quasar. These 4 points are actually the same quasar, imaged 4 times, been around a galaxy in the foreground. Lined up just right. There are a few of those that have been found. Now, even if the Earth was fixed in Robert's model, the force of the universe going around it would cause it to wobble a little bit, at least. Stars wobble if they have planets around them. This is how gravitational microlensing detects exoplanets. Gravitational microlensing for finding exoplanets relies on relativity being true. About 100 exoplanets have been detected using that. So it has a lens in the foreground, the planet, and the star will change according to that. And the speed of light has never been observed to change faster. This is pretty expensive experiment if you want to do that yourself. I'm not in any financial situation to waste money on a speed of light experiment, but there it is. And I believe Robert has to have problems with going to the moon if the Earth is the center, because that would rely on heliocentric data. So in October, November 1977, this was after Apollo, but these experiments were left there. The Soviet radio telescope Raton 600 observed all 5 transmitters of the Apollo lunar surface experiment packages, excluding Apollo 11, because Apollo 11 was far more primitive and it died before this date. The data was all in alignment with NASA's. Now, why would the Soviet Union confirm that NASA went to the moon if they if there were our arch nemesis, and they would love any opportunity to say they didn't really go, it was a hoax. And in the video Einstein, Closet Geocentrist, one of Robert's videos or movies, he claimed that light travels faster through a medium, ether, but observations show that light will always flow through a medium, such as water or a prism. Why would this other medium somehow increase the speed of light? And I got some other stuff for some discussion, but that's, let's see, hang on a second. I need to stop sharing the screen. How do I stop sharing the screen? There we go.
Oops.
Okay.
You're good. Is that it for your opening,
Okay.
Jackson?
All right. That's the opening. We'll leave it there.
Okay.
Now, yeah.
Yep. Anytime we don't use, no worries at all. We can always toss that into the audience Q&A. So that was just over 9 minutes. I appreciate it. We're now going to hand it over to Dr. Robert Sungenis. And so, Robert, whenever you're ready, you have 12 minutes. The floor is yours.
Okay, so just one comment on your opening is the fact that you cover too much material. You've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21 topics. Okay, now that's going to be impossible to do a thorough job that I would have to do on each of those topics, because my 12 minutes has to be to give my side of the story, and then the rebuttal, I'm supposed to rebut 21 topics. Okay, so this is what I call the shotgun approach, where you just bombard the other side with, dozens, almost literally 24 topics. Okay, what I would have suggested if I had a time to talk to you before is pick your top 5. Pick your top 5 where you think that, geocentrism is not scientific or even viable or possible. And I could address those. Okay. So if I don't address any of these in the rebuttal, it's not because I can't answer them. It's because there's too much material here. Okay. So, I mean, if we had a 10-hour debate, I could do so, but not with this debate. So I just want to mention that up front. I've been in many, many debates, so I know the good and bad ways to approach them and to present them, and that's why I had to mention this. All right, so what I want to do is something I don't normally do in a debate, but I'm going to read from some top scientists, and this you can get in my book, Geocentrism for Dumpskis, right at the beginning of the book, what they say about this topic. Okay, because I'm just me. I'm not a famous scientist. I'm just following what these guys have said. That's how I started this whole thing. Is what do the top scientists admit? Even if they don't prefer a geocentric universe, do they admit that it's scientific and viable? Yes, all of them do. Okay, so I haven't met one that doesn't. I really can say that honestly. Okay. So like, for example, the first one here is from Albert Einstein. He says, to the question whether or not the motion of Earth in space can be made perceptible in terrestrial experiments, we have already remarked that all attempts of this nature led to a negative result. In other words, they have tested whether the Earth moves or not, and they can't tell you scientifically that the Earth moves by proof. Okay, that's coming from Albert Einstein. Lincoln Barnett, who is a historian, scientific historian, whose book was, the foreword of the book was written by Albert Einstein himself. He says in there, we can't feel our motion through space, nor has any physical experiment ever proved that the Earth actually is in motion. Okay? And these are all documented. You can find the sources for them. Read them yourself. Here's another one from Stephen Hawking. So which is real, the Ptolemaic or Copernican system? Now, we wouldn't use Ptolemaic, we'd probably use the Tychonic. But the point is being made that we can't tell which one is real. Although it is not uncommon for people to say that Copernicus proved Ptolemy wrong, that is not true. One can use either picture as a model of the universe, for our observations of the heavens can be explained by assuming either the Earth or the sun to be at rest. Okay, that's from his recent book before he died in 2010. What's it called? The Grand Design, I think that book is called. Here's another from Fred Hoyle, famous astronomer in the 40s and 50s. He said, we can take either the Earth or the sun, or any other point for that matter, as the center of the solar system. This is certainly so for the purely kinematic problem of describing the planetary motions. It is also possible to take any point as the center even in dynamics, although recognition of this freedom of choice had to await the present century. Okay. Now, my opponent had referred to this in his first slide about Jupiter being the center, and that's certainly true. Okay, but what that does, it puts a hole right in the stance of science for the last 400 years, because from Newton, Galileo, Copernicus, Kepler, everybody, they said it wasn't possible to have the Earth in the center. But Albert Einstein came along, and before him, Ernst Mach, and they said, no, can't have that anymore. Although we can't tell you which one's in the center, okay, both Mach admitted that and Einstein admitted that, we can't say anymore that the Earth can't be in the center and not moving, okay? That whole science thing from Newton has drastically changed by the time we get to the late 1800s and into the 1900s, okay? So now the next question would be, well, if it's possible for the Earth to be in the center and not moving, how would we go about proving that, or at least giving evidence for it? Because proving something in science is very hard to do. How can we give evidence for that? Okay. And so let me see if I should read any more of these. Oh, I think there is one here that really stands out because it comes from Isaac Newton himself. Okay. Now, Isaac Newton thought that he proved that the Earth was revolving around the sun. Why is that the case? Well, because he confined his system to the solar system. And if you just deal with the solar system, the sun and the planets, the Earth will have to go around the sun. Why is that? Because the sun is bigger, has more mass, and therefore it has more gravity. And in order for the Earth or any planet not to be pulled into the sun by its gravity, it's going to have to revolve around the sun and go fast enough so that it doesn't get sucked into the sun, and slow enough so that it doesn't go out into space. It has to go around in an orbit. Okay. And you can make calculations with with Newton's F equals ma, And you can tell how fast that planet has to go depending on how far away it is from the sun. It's very easy to get those equations to work. The question is that the reality? Okay. You can put math to anything and make it look like it's viable and it's scientific and it's very persuasive. But what we know is 2 + 2 = 4, but so does 3 + 1. You both get to 4. The question is, who has the right addends? Are there 3 apples and 1 orange, or 2 apples and 2 oranges that make the system work? Okay, and everybody can understand that. But here's what Newton says. He says, in order for the Earth to be at rest in the center of the system of the sun, planets, and comets, there is required both universal gravity and another force in addition that acts on all bodies equally according to the quantity of matter in each of them, and is equal and opposite to the accelerative gravity with which the Earth tends to the sun. Since this force is equal and opposite to the gravity toward the sun, the Earth can truly remain in equilibrium between these two forces and be at rest. And thus the celestial bodies can move around the Earth at rest, as in the Tychonic system. That comes from Isaac Newton himself. So as much as he thought he proved that the Earth went around the sun, he realized that, hey, you know what? I don't know all that's out there. And if there are sufficient forces outside our solar system, yeah, it's very possible that the Earth could be in the center and everything's revolving around it. Now, that answer to Isaac Newton's question didn't come until about 200 years later. He published his Principia Mathematica in 1687, and it wasn't until 1887 when Ernst Mach came 200 years later and said, Newton, sorry, bud, you can't assume that there are no forces out there that are going to affect our solar system. And if that's the case, then we can put the Earth in the center and have everything revolve around it, as long as we have sufficient forces. Then Einstein came along with general relativity, and the very nature of relativity made him realize that either the Earth is revolving around the sun and rotating on its axis, and the universe is still, it's fixed, or because of relativity, the Earth can be in the center and not moving, and the universe itself revolves around it. Now, that wasn't just a thought that he had. If relativity is true, he had to figure out the mathematics behind the geocentric universe that he just gave sanction to. And he did. And there's a lot of other people that did so after him. Like, let me see, Julian Barber, and his scientific partner Bertazzi wrote a paper about almost 30 years ago that showed by mathematics how the geocentric system would work under Einstein's general relativity. There's been about a half a dozen others who have wrote papers similar to Barber and Bertazzi who have proven the same thing. Okay. Now, I know what my opponent's objection is going to be. Well, you can put anything in the center and make, yeah, you could. Okay. But what we're doing first here is showing that all these claims from Galileo, Newton, and everybody before relativity that the Earth couldn't be in the center, because the debate title that we have chosen is Geocentric Universe is not possible, okay, and not scientific. Well, I've just shown that that's totally false, and I haven't even gotten, halfway into the debate, because all these scientists have agreed, no, it is scientific and it is possible. The question is, can we show now the evidence that the Earth is in the center and not something else? Okay. And that will be another part of this debate. And most of my opponent's theses that he covered in his opening statements deal with that issue. Okay. Can we show that the Earth is in the center, not moving? So, Donnie, I need to know how much time I have for this opening.
You have exactly 2 minutes, Robert.
2 minutes. Okay.
Yeah.
So I can say this, if I had to deal with all 21 of these theses that tries to deny the resolution that we have agreed upon, in the sense that now we have to show evidence that the Earth is is the center, okay? Because I've already proven that all the major scientists have said that it is possible, and it's scientific, okay? Now, if you asked Albert Einstein, well, Albert, which one of those two that you just admitted are scientific and viable? That is, the Earth revolving around the sun and rotating on its axis, or the Earth being fixed in the universe and the universe not moving. Which one of those two do you like? What do you think he would say? Well, of course he's going to say, the Earth revolves and rotates. Why? Well, because he's a man of the world. Okay. No scientist in his right mind is going to say, oh yeah, for the last 500 years, we've been under a delusion that the Earth is revolving and rotating when actually it's, in the center and not moving. None of them will do that. What they will say is and Stephen Hawking does the same thing. He'll say, well, now it's a philosophical preference. Philosophical. Which one do you like the best, since both are possible? And since most of these scientists are atheists, they have nothing that would move them to the other side, they're going to agree, okay? Because they know that as soon as you put the Earth in the center, that means somebody had to put it there, because it's not going to get there by itself. The odds of it getting there by itself are astronomical, okay? So why are they scared about that? Well, because if somebody put it in the center, that means that somebody has to be bigger and better than us. And we usually put the word God on that. And they're very fearful of God, because God says, I don't like the way you're living, and I'm going to judge you for your sins. And, the results of that punishment. So let's get God off the stage, and we'll believe in the heliocentric model, and that will make us safer.
Okay, Robert, very good. I appreciate that opening statement. That concludes the opening statements for tonight's debate. To the audience, if you do have a question for our guests, again, just make sure it's on topic, and make sure to tag me, either at Standing for Truth or at Donnie. Okay, Jackson, we are now moving into our first rebuttal for tonight. Our first rebuttal is 8 minutes. And so whenever you're ready, please let me know. And the floor is yours.
All right. I don't think I'll take 8 minutes, but I didn't mean to bombard with points. I said so much time to prepare for this. I just came up with a lot of them. Having said that, you didn't really choose any of the points, I feel like, really. You might have chosen one a little bit. But, some of the physics are viable for a geocentric universe, but some of the physics are viable for anything in the center if you put it in the center, which you said I would say that, but that's true. And there's a lot of appeal to authority fallacy going on there. And let me see what I have here. You can apply math to anything and make it make sense. I mean, that's true to a point. To address one thing, exoplanet orbits. Why do all exoplanets orbit their stars, but not all? But the sun orbits us, our planet. And another thing, Earth can't be static even in your model, because the force of a universe going around the Earth would cause it to wobble, and even if it was the center, so it can't be static. And last thing, really, there's not much to address yet, but the last thing, I don't think that God's impossible. But even if there is a God, I think the Earth is not the center of the universe, or at least not the center of the solar system. So that's really all I have to say for the first rebuttal. That was a minute or two, but that's what I got for the first
Okay, keeping it short and sweet, Jackson. We are going to throw it right back to Robert sungenis now. And so, Robert, you do have 8 minutes for a first rebuttal. So please, whenever you're ready, just let me know. The floor is yours.
Boy, can I take the 6 minutes that he left over?
We're going to give you a 14-minute rebuttal.
All right. So, okay, let me start. Now, in an opening statement, I don't have to choose any of your points that you made. I'm here to make an opening statement that represents my view. So I could have skipped all of your 21 points in an opening statement. You deal with the opponent's points in the rebuttal. Okay, so it's not that I purposely avoided it. It was just I needed to make the comment about the shotgun kind of approach. But I have to say this, even in your 21 points, I didn't see any explanation that would convince somebody that, oh, yeah, that proves that the Earth is not in the center and it's not moving. I didn't get that from any of your points. I have to be honest. I knew what you were saying, okay, but you just sort of just said something. Well, this occurred, this occurred, this occurred. So that proves. Well, it doesn't unless you explain how it proves it. Okay. So that's why I'm saying if you had taken 5 points and you laid out your facts and then you explained why this makes geocentrism impossible, then I would have a lot more to chew on and debate. Now, the next thing you said was I'm using the fallacy of authority. Okay. But I mean, come on. Our top scientist, I mean, as a matter of fact, I can't find any scientist who doesn't agree with all the quotes that I read, that it would be impossible for geocentrism. They all know it. Okay. So you might throw in, okay, well, he's appealing to authority, and that's a logical fallacy. Okay. In the technical sense, I would agree with you. Okay. But in the practical sense, I think even you would have to agree that if Albert Einstein, Stephen Hawking, Fred Hoyle, and I have about 30 other quotes here from different scientists throughout that are famous scientists. Even Newton himself admitted it. Okay. Now, what more do you want? All right. The reason I read those is because if I come on here, Robert sungenis, a nobody, and I start giving facts and figures about geocentrism, everybody's going, okay, who's this guy? But so I tried a different tactic, and I showed all the scientists who say the same thing, and that's where I got it from. I got it from them. Okay? When Albert Einstein says, yes, geocentrism is possible, I just don't prefer it, I listen. Okay? When Fred Hoyle says it, when Newton says it, I listen. And that's where I'm coming from. Okay? It's not something I made up myself. As a matter of fact, I don't go the distance that other people do, like they believe in the flat earth and they believe in aliens on, different planets and all this stuff. Not me. Okay? This is the only weird thing that I believe in. And that's because all these scientists are saying the same thing. They just don't want to have it. They don't want geocentrism because they know the implications. Now, you made a mention of that. You said, well, even if God exists, that doesn't mean the earth has to be in the center. Okay, I agree. Okay, but that's not what we're debating. We're debating that if the earth is in the center, why don't these scientists prefer to go in that direction? That's what my point was. Because if the earth is in the center, the only way it could be is because God put it there. Somebody put it there. Okay, because that makes us special. The whole movie, you saw the principle. They don't want us to be special. Lawrence Krauss was out there crying, well, we don't want to be special. Well, I can understand why he doesn't want to be special. Okay. He wants to live here and go, and there's no more Lawrence Krauss because he doesn't have to be responsible to God. Yeah, I understand that. Okay. So what else you said? Earth can't be steady because of the wobble. Says who? Not Einstein. Not Hawking, okay? Because the Earth is a center of mass. So whether the Earth has a wobble or not, everything's going to be balanced out because the Earth is the center of mass. Okay, even a gyroscope can have a wobble. You run that gyroscope and then you touch it with your finger, it's going to start wobbling. But the center of mass never changes. Okay, it's going to wobble around the center of mass. And there are even more things I could say about why the Earth is in the center and doesn't move. And that deals with inertial forces, which if I have time, I'll get into later, but I'm not going to do it now. Right now, I just want to answer your objections. And you said, the other thing that you said was, why do exoplanets orbit their stars, and yet we're the only place in the universe where the star orbits the planet? Okay, good question. I think it's almost self-explanatory, because every one of those exoplanets is outside the center of the universe. If the center of the universe is where the center of mass is, that means it's not going to move. All those exoplanets, they're not anywhere near the center of the universe or the center of mass. So they're going to be local systems that are dependent on the local bodies that are in there, and whatever is in there dictates from physics what's going to go around what. Okay, you even see binary stars going around each other. Okay, so all those local systems out there are going to be totally different than the system that's at the center of the universe, where the center of mass is. Now, to understand this even better, you can take the Earth out of the system. Let's pretend there is no Earth, but you have a universe, it's a sphere, and it's rotating. Does that rotating universe have a center of mass? Yes, it does. Is anything there? No. It's just a theoretical point called the center of mass around which that universe revolves. Okay? Everybody, Physics 101, everybody will understand that. And that center of mass will not move. Okay? Now, let's take this little Earth that's a pea compared to the size of the universe and put it in that center of mass so that it occupies the same space as the center of mass does. Okay? Can that universe still go around that little pea? Certainly can, because it occupies the center of mass. Will all the other local systems in the universe, the stars, binary stars, or exoplanets, whatever, will they be in that situation? No, because they're all outside the center of mass of the universe, that is. Okay, so that's easily explained. How much time do I have?
You have 1 minute, Robert.
1 minute. Okay, so let me see if there's any issue in your points, your 21 points, that I could explain in 1 minute. Oh, well, this has nothing to do with it, but I do believe in black holes. Okay. But black holes aren't going to change anything. If black holes exist in the heliocentric system, they can exist in the geocentric system. Okay. So that's no problem. As far as speed of light, probably is an issue we should cover, because if you read Einstein's general relativity, now you said you read material and you've been working on it. Apparently you haven't come across the statement Einstein made that the speed of light is not constant in general relativity. In special relativity, yes, it was constant. Why? Well, because there's no gravity and there's no inertial forces. You have a pristine environment in special relativity where there's no ether, there's no gravity, there's no inertial forces. So yeah, light's going to be constant. That's just common sense, because there's nothing to impede the light and there's nothing to make it go faster. But if you read general relativity, it's just the opposite. Light speed is not constant. It can go any speed depending on the environment that it's in, including gravity and inertial forces. And ether, you can throw that in there too.
Okay, Robert, thank you very much for that roughly 8-minute rebuttal. Gentlemen, that concludes the openings. and the first rebuttal. We now have a second rebuttal. To the audience, yes, I am all caught up on the questions that you've sent in. I appreciate everybody keeping the questions on the topic of geocentrism. Okay, Jackson, we're going to hand it back to you now. And for our second rebuttal, we have 5 minutes this time instead of 8. And so, Jackson, whenever you're ready, the floor is yours. Go ahead.
All right. Maybe I didn't connect the dots well. I'm not sure, and black holes maybe is one area I thought I read some material where you didn't agree with black holes. That's my bad. But you didn't really explain much of what points weren't convincing or why, really. Now, sure, you can make some of the physics work for Earth being at the center, but you can make it work for Jupiter being at the center. I contend that Jupiter is the center, and you can't tell me I'm wrong because the physics can work for it. But I mean, you'd have to deny a lot of things, space probes, the Apollo missions. For this, you'd have to be. You say the only conspiracy you have is, or not conspiracy necessarily, but good strange view that you have is geocentrism. But you have to deny a lot of things about human space flight or space probes in general. So Voyager 1 and Voyager 2 visited all the gas giants. They had to make course corrections and gravity assists, and they couldn't have done that if NASA knew or didn't know where the sun was. So either NASA knows that the Earth is the center and they're keeping it secret for some reason, or they're faking everything, or the sun is in fact the center. Now the wobble, and you said the center of mass. I don't understand how the Earth could be the center of mass. You can say it's the center, but how is it the center of mass? It's as massive as the sun. It's not. It's way less massive. It's as massive as the universe. It's not. It's way less massive. Now, the speed of light being constant, and you mentioned ether. Now, ether, you contend that ether is a medium where light can speed up through. But as I mentioned, every other medium light enters, like a prism or any kind of glass, water, crystal, it slows down. So what are the physics behind ether being this medium that can make it speed up instead of slow down? And that's all I've written down. So I'll hand it back to Robert or Donnie, whoever takes it. So.
Okay, Jackson, thank you very much for another short and sweet rebuttal here. Let me restart the timer. And okay, Robert, we're going to hand it over to you whenever you're ready, and you've got 5 minutes for a second rebuttal.
Okay. Thank you, Jackson. So black holes. When we first started this thing in geocentrism, and it's been, 20 to 30 years or so, we question the existence of black holes, okay? Because all you see in those photos is a ring of light that is going around a black whatever it is, okay? Now, the question is that a black hole? In other words, we see the black, we see the light around it, but is it the black hole that's required by general relativity? Because general relativity, and Hawking said this himself, the mathematical result of general relativity is that we're going to have black holes. Okay. And so they've been trying to prove general relativity by saying that those rings of light that we see out there with the dark in the middle, that's a black hole. Okay. Now, we question whether that was true or not, because you may name it a black hole and you may have all your theories about black hole from the mathematics, but is that a black hole that we're looking at? Okay. That's the reason we had questioned it. Regardless, it doesn't make any difference. Those black holes or whatever those things are with the rings of light around the black center, they can have in the heliocentric system or the geo. It doesn't make any difference whatsoever. Okay. So we don't go there anymore. Now, you were talking about ether. Let me start from the bottom. I'll go up. The fact is that Einstein in his general relativity took the ether back the very ether that he rejected in special relativity in order to keep light constant, the speed of light constant, was the very ether he took back in general relativity when he said light is not constant. Okay? Now, granted, ether or any substance that's in space, whatever space is, and it's not nothing, it has to be a something, because nothing doesn't exist. It has to be something, and it's going to affect the speed of light. Okay? Ether, schmether, whatever you want to call it, doesn't make any difference. Okay? And that's why it's 186,000 miles a second when we measure it on Earth. The question is, what happens to that space when you get out into the universe that's spinning around very fast? Well, Einstein himself said you have the inertial forces from a rotating universe, the centrifugal, the Coriolis, and the Euler forces are going to affect the space and make it such that the speed of light is going to increase because of the nature of that space. That's what his equations say. That's what Barber and Bertotti found out. That's what all the guys that use Einstein's general relativity found out, that the light is going to exceed c, and it may go 3c, 4c, 5c, 6c. And why is that a big puzzle for big bangers, for example? Because they believe that the universe is expanding at 4c, 4 times the speed of light. Okay? Well, how is that possible? Okay? When if light speed is the maximum, how can we be going faster than the speed of light? They even say that for inflation at the beginning, that the universe didn't explode at 186,000 miles a second because that would be too slow. And so what they do is they add inflation in there. And how can they add inflation? Because general relativity allows them to do it. Why? Because general relativity says things can go faster than the speed of light. Okay? So at both ends of the spectrum, at the beginning and at the end, they have things moving out faster than the speed of light. So all this talk about things can't go faster than the speed of light, that applies to one area, special relativity. I see I don't have much time, so I got to get moving here. You said you don't understand why Earth could be at the center of mass. Why not? Okay? If you agree there's a center of mass to the universe, why can't someone stick the Earth in there and match the Earth's core with the center of mass for the universe? In other words, the universe and the Earth share a center of mass. Why wouldn't that be possible? Okay? I mean, you just stick it in there. It's possible. All right. Voyager 1, you said they need to know where the sun is. Well, of course they do. But you see, we have the same map that the heliocentrists do. It's called the neotychonic universe or solar system, in which every planet that you have calculated where it is, and the sun where it is in the heliocentric system, we have the same map in the tychonic system. Those planets and the sun are in exactly the same place. Okay? They just move around differently. That's all. No difference. So yeah, you'd have to know where the sun is, and we would too in the geocentric system. So there's really no difference at all. You mentioned space probes. You said I would have to deny. No, because we're going to use the same physics, the same Lagrange points, okay, that you use in the heliocentric system to put the W map at Lagrange point 2, because we know what the gravity is. And that gravity can all be calculated in the geocentric system. You don't have to have the heliocentric system to do it. Okay? So there's a couple other points you had here, but I don't have any time.
Okay, very good. Robert, I appreciate that rebuttal. Gentlemen, we're moving along smoothly. That concludes the openings and our 2 rebuttals. What we'll do now is enter a focused discussion. We'll take one point at a time. We'll try and make sure we get through as many of the relevant points as we can over the next 30 minutes. And so, Jackson, since you're in the affirmative and Dr. Sungenis just ended with his second rebuttal, why don't you pick one of what you believe is the most pertinent points for this topic, and we'll start there. We'll go back and forth on that. Go ahead, Jackson.
All right. Let's talk about the lunar retroreflectors and the Kennedy Thorndike experiment, which It's just the Michelson-Morley experiment, which tried to disprove ether, but this one uses two different mirrors at different lengths instead of the same length, like the Michelson-Morley. So they used the lunar retroreflectors to do a Kennedy-Thorndike experiment. And not only does this prove relativity, but it kind of shatters ether as well. Now, I don't know if you accept that the lunar retroreflectors are actually there or not. Or
Let's just say I do.
Okay. Let's just talk about that for a minute then.
Okay. So you're going to have big problems because the Michelson-Morley, Michelson-Gale, Kennedy-Thorndike, you name it. There's 12 different experiments. They are all very sensitive. Okay. Like the Michelson-Morley experiment, 1887, it could pick up vibrations from people walking on the sidewalk 100 yards away.
Mm-hmm.
Okay. So if you're going to try to make a Kennedy-Thorndike experiment with a celestial object that is moving, the moon, number one, and is 240,000 miles away, number two, and it takes light, what? How many seconds? 1.5 seconds or something. I mean, you're going to have big problems. So if you can't prove anything by all the interferometer experiments that were already done from 1881 to 1930, what do you expect to get from lunar reflectors that if the moon is moving, there's vibration there, and you're not going to get an accurate result? Okay. Now let me back that up by saying this, and you can come in. The ether issue is even the Kennedy-Thorndike experiment had, I think it was like 1.5 kilometers per second result. Okay. And the fact is that every interferometer experiment that was done all had a positive result. It was very small, but they were all positive. So what's causing that positive result, even if it's small? Okay. That's one issue. The second issue is, the reason all the scientists say, well, they all had null results. Why? Because they already assume that the Earth is moving, you see. And if you assume that as the foundation for your experiment, and you come up with a ether resistance that is 1/10 of what you expected, then how are you going to explain that? Well, here's the way you do it. You do it the way Einstein did. You say, well, there is no ether, and the positive result they found, that's just marginal error. Because they already assumed the Earth was moving. Now, then let's say you assume the Earth isn't moving, and you get this very small result that is nowhere near the Earth moving 30 kilometers per second around the sun. Okay? Well, you would just say, yeah, that's because the Earth isn't moving. That's why they didn't get a big result that they were expecting, you see? So everything depends on what you assume at the beginning of the experiment.
All right. Well, the physics of the moon in motion and its distance can be calculated with the retroreflectors itself. So, I mean, they know this data, and they can account for these vibrations or whatever. So the Kennedy-Thorndike experiment with the lunar retroreflectors, I think, is a good example. But I mean, yeah, they're very sensitive. I've seen videos of some of these interferometers. You step on the floor and the fringes move, but they can account for all this too.
But not to 30 kilometers per second. See, if the Earth is moving around the sun, you're going to have to get interference fringes that are in accord with 30 kilometers per second. No interferometer even came close to that. The highest one we ever had was Miller's experiment, and he did 100,000 experiments, was between 5 and 8 kilometers per second. And he needs 30. If the Earth is revolving around the sun, he needs 30. Okay? So whether it's the, Kennedy-Thorndike or whatever one it is, they have never shown evidence that the Earth is moving.
there's one experiment, I forget the name of it. They put lead bricks between the interferometers to try to block the ether wind. I don't know what model of ether you subscribe to, but it doesn't matter if you do that experiment without that or with the lead blocks. There's never, ether seems to be imperceptible, and that's what I was kind of getting at with my kind of not so precise experiment in the tunnel.
Yeah, well, see, that all was true until Michelson-Gale came along in 1925. And what did they do? They used the same interferometer that Michelson used in 1887, but they reoriented it so it would calculate the rotation of the Earth instead of the revolution of the Earth around the sun. And what did they come up with? 98.7% positive result. That the Earth was rotating based on an interferometer that was calculated by ether resistance. Okay, or whatever you want to call it. Like I said, you can call it Schmeether or whatever. It doesn't make any difference. Yes, it's imperceptible. That doesn't mean it's not there. Something was in that interferometer to make them calculate the exact sidereal time rate that the Earth is revolving in that experiment, 1925. Okay, whereas Michelson-Morley didn't have any such luck. Now, we can explain that as geocentrists. Why? Well, the Earth isn't revolving around the sun, number one, but something between space and Earth is moving at a sidereal rate of 23 hours, 56 minutes, and 4 seconds. Something is making it calculate that difference in movement. Whatever it is, I don't care what you call it, they calculated a difference. And we can explain that as a geocentrist because if the Earth is fixed and the universe is going around it, there it is. That's what caused the result of the Michelson-Gale experiment. Okay? But as a heliocentrist, that is not going to be satisfactory for you because why? Because you need a rotation and you need a revolution. You have to have both in order for your system to be correct. And if you can't get a revolution out of the interferometer experiments, but you got a rotation, then your theory's falsified because you need both. You can't have one. Only the geocentrist has to have one.
All right. That kind of goes into my slide about the Chandler wobble, which the rotation of the axis of 430 something days, but also the rotation of the Earth every 24 hours or so. Now, if ether, the universe, all this was moving around the planet, it could account for one of those, but it couldn't account for both.
Why do you say that?
Because either it's causing a 24-hour rotation or a 430-day rotation. It can't cause both.
Well, it's a Chandler wobble. It's not a rotation.
Well, it's a wobble, but it's rotating on the axis.
Any wobble is going to precess to the point where it's going to go around in a circle. That's where the axis goes around in a circle. But that doesn't mean it's a rotation. It just means the axis is going around. That's all.
All right. Now you mentioned Lagrange points. Now, I think in your model they wouldn't quite be the same because the sun has to be in a strange position in comparison to a geocentric or a heliocentric model. I've seen a couple different animations you've put out of the sun either being like below the southern hemisphere to account for seasons, or it kind of moves, like an S pattern around. So I think Lagrange points would be incredibly unpredictable if they existed at all in your model.
All the Lagrange points would do is go up and down a little. They would go up and down in the same percentage that the sun would go up and down, but they're going to be in the same position. And right. you could calculate the vertical movement of the Lagrange points, and they're not going to change in comparison with the sun. They're all going to be the same. So they're all going to move at the same time.
Don't you think they would have known that for WMAP, Planck, and the James Webb Telescope and L2, and would have had to account for it?
Well, yeah, but have they ever talked about it? No. So, yeah. I mean, you have to find evidence that they had trouble with the vertical movement of Lagrange point in order for you to present that as evidence. That may be something you want to research.
I think they haven't talked about it for a good reason.
Well, they haven't talked about, let's talk about the GPS.
Hmm.
They haven't talked about the fact that the speed of light is not constant in the GPS for good reason.
Right.
Why? Because that will destroy special relativity. That's why.
No, it's because the satellites are moving much faster than what's on the ground. That kind of is a feature of relativity.
I don't understand what you're saying. Are you saying that the GPS satellites are moving at speeds that separate them?
Speed is increasing time dilation.
Oh, well, you have to assume time dilation. You haven't proven that.
Well, that kind of proves it. The whole GPS system proves time dilation.
No, because those GPS satellites that are there, they're at the same distance. They never separate those distances. If they did, every one of our GPSs on our cars would be out of whack.
You mean the same distances as like horizontal distance or vertical, so to speak?
Yeah, you just
the GLONASS.
Get a plumb line from one GPS satellite to the other. That distance is going to be the same. Okay.
Except for the GLONASS satellites, which are different than the GPS.
All right, well, let's just deal with these for now. Here's the fact. When you shoot a light beam from one GPS satellite in the east to a satellite in the west, okay, and I'm going this way, so I don't know what your east and west is, but let's just say it's going this way. They have a certain speed for that, okay? Now, when they shoot a light beam from the west to the east, they have a different result every day, 24/7.
That's right.
Okay. Why is it always the fact that whenever they shoot the light beam from the east to the west, it's always a shorter time period for that light to travel than when they shoot it from west to east?
Because the Earth is rotating.
Well, how would that make a difference? How does the light beam know that the Earth is even there?
Because the gravity is still impacting it.
Well, then why does the gravity affect it one way and not the other?
Because it's spinning.
Because it's spinning. So gravity spinning is going to have a difference on the speed of light?
I would think so.
Okay. Do you have any scientific facts behind that? Has anybody ever shown that?
Can I pull the math up on it? I don't think so at the moment, no.
Okay, so I know gravity will affect the vertical, okay, in the sense that it could pull the light beam down. But whether a rotating gravity object is going to affect the speed of light going horizontal, that's something you're going to have to prove.
That kind of goes back to the Halley-Keating experiment with airplanes going east and west. Got the same results, yeah, but I mean, this again proves time dilation.
No, it doesn't, because if you're in a plane and you put a cesium clock in a plane, you're going to have a lower gravity potential in that plane than you do on the ground. Mm-hmm. That's just a fact.
Sure.
So if gravity affects the rate the cesium clock ticks, then you're going to have a slower time in the airplane than you will on the ground. And so what they do with that, instead of recognizing that, they just say, oh, we just have time dilation. We have two different times. Well, why? Because the gravity affected the ticking of the cesium clock. That's why. Okay. So that's all you're doing. So the Halley-Keating experiment proves nothing.
All right, it proves nothing. So general relativity and special relativity, you talk about that a lot. General relativity is just kind of an expansion on special relativity, right?
Well, it depends on what angle you're dealing with. I mean, it's a semantical thing. What do you mean by that?
I mean, you're basically saying yes, but without explanation.
Well, you want me to go into it? I will. Okay. The difference is that the special relativity has no outside effects. It's a pristine environment without gravity, inertial forces, ether, anything. Okay. And in that environment, I admit, yeah, why would light go any different speed in a pure environment like that? Okay. Now you're getting, and so Einstein realized that. And he used special relativity to answer the Michelson-Morley experiment. He says, how is it that if the Earth is revolving around the sun, we're not getting any ether resistance? Well, because ether doesn't exist. Well, that's easy to say, except the fact that Michelson Morley did have a positive response. It just wasn't the one that Einstein liked. Okay, that would give him a revolving Earth. All right, so you have this pristine environment in special relativity. Now he realizes that that's not going to work in the real universe. Why? Because the whole universe is filled with gravity. And he says it's filled with gravity everywhere. There's no place that escapes gravity. Now, if that's the case, then the speed of light is never going to be 186,000 miles a second. Never. Because gravity is in every sector of the universe, and it's going to affect that speed. Okay? And then in his geocentric model, he also has the inertial forces to deal with, not just gravity. And they're pretty powerful. He says they're so powerful that they equal gravity. So you have to deal with them too. And when you do that, wow, that changes everything. And then he says, well, you know what? I made a mistake in taking the ether away in special relativity. I have to bring it back in general relativity. Why? Because then light wouldn't have a medium to go through. Those are his words. So we got two contrasting, virtually contradicting theories from the same guy. Okay.
Well, space isn't nothing like in the heliocentric model. It's even in there's no such thing as a perfect vacuum. Like even there's specks of atoms here and there everywhere. But what evidence is there really that there is this medium in space called ether? I mean, there's some anomalous results from some interferometers, maybe, but what really?
They're all around the same. They all have around the same resistance. Like Kennedy Thorndike might be a little lower, Miller's a little higher, but the averages are about 4 to 5 kilometers per second, all of them. And they're nowhere near the 30 kilometers per second that's needed for a revolving Earth. Okay. But, this all started back with the Greeks. They're looking at space and they're saying, what is it? They see a candle lit and they blow it and the candle goes out. So they know that something exists to blow that candle out that they can't see because you can't see air. And so they just develop their thought from that. Well, what's holding the air? Because the air can't be the smallest thing because I can feel it. It's like we know it's there. So what they have in quantum mechanics now is the fact that if you get down to the lowest order of substance, you end up at 10 to the minus 35 meters as the length of those particles, whatever they are. That's all we've gotten in science so far. We can't go any further. Okay. So it's either going to be that or something similar to that. But we do know this, that nothing doesn't exist. So you can't look out into space and say, oh, there's nothing there. No, there is something there, because if it was nothing, then all those celestial bodies would coalesce with the Earth and we'd be one big ball. Okay. There's got to be something between the Earth and the moon or the Earth and the sun. And we say, okay, that's filled with this quantum mechanical ether, whatever you want to call it. It has to be something. That's all we know.
I mean, angular momentum and the orbits keep them from falling into each other. It's not ether. And that goes back to.
I didn't say it was ether. I didn't say it was ether. Yeah, I believe in angular momentum.
Okay.
As a matter of fact, that's where the inertial forces come from the angular momentum of the universe.
All right. So is ether a particle or what is it?
We think, it's the smallest particle possible before it's no longer a particle, no longer matter.
Okay. So why is CERN or some other particle accelerator experiment not detected any hint of such a particle that is so fundamental to the universe?
Because they don't have enough energy to break the proton apart. That's why.
They can get quarks and gluons, and they can see those.
And they can theorize that, but they've gone no further than the gluon or the quark or anything else. Okay. The question is there anything beyond the quark? They just don't have the power. That's why they want to make a bigger one, to try to accelerate it even more.
But so far, there is no evidence from a particle accelerator of anything like.
No, but you theorize what it is. You take the mass, the energy, everything, you put it in an equation. That's what Max Planck did. He was the first one to do that. And that was in 1927. And they all knew that there had to be something out there. And then it developed into quantum mechanics, and you got Schrodinger's equation that tells you basically what the size of the particle is. And it has to be 10 to the minus 35 meters. Okay. But I admit it's all theory. It's all mathematics.
But if there is something smaller than quarks and gluons, and there may be, that doesn't make it ether. That doesn't mean it's a fundamental. I mean, it's probably fundamental in some way, but does that mean it's everywhere in the universe? Because I feel like if you're splitting apart these subatomic particles to see ether, then the subatomic particles have to be, or the atoms have to be everywhere in the vacuum of space for this to make any sense, does it not?
Oh, sure. Yeah, they're going to have to occupy, in other words, the ether, whatever we're going to call it or envision it to be, is space. Okay. And so the next question is, well, how would we move through it? Well, quantum mechanics has a way to explain that. It's called wave mechanics. That's how you move through it. Okay. But to answer your question, yeah, it'd have to occupy every space, but space would be ether then.
But then there would be no vacuum, because we're saying these particles, these ether particles, are inside subatomic particles, which are inside atoms. So how is there a vacuum?
There is no vacuum. Vacuum is just a name we put on something that's more discrete than what we experience on Earth.
All right, so there's no vacuum in space.
If you open up a can of peas, yeah, there will be what you think as a vacuum, okay, but that's just a name that you're applying to this effect that you see. That whatever is out there is much more condensed and discrete than the air we have on Earth.
So what I'm saying is, for ether to exist, there have to be atoms everywhere in the vacuum of space for ether to occupy these ether particles.
No, not necessarily. I mean,
well, you said we can't detect. We have to split apart the protons and the gluons to see the ether particles. So,
well, just because the ether is in the proton doesn't mean the ether has to be in the proton. It can exist independently of the proton. Okay, that's why when we look out in space, we find that it's about 90% hydrogen, but the hydrogen is spaced out. You might find one atom of hydrogen, and 10 miles later you might find another. Okay, so yeah.
But hydrogen atoms can exist on their own, and you're saying that the ether particles are pretty much fundamental to atoms in
right.
A sense.
That's right. Ether would permeate everything.
Right, but you're saying, okay.
Now, the question you would have to answer, though, is why Michelson-Morley or any interferometer experiment that's supposed to be measuring the revolution around the sun of the Earth is not getting what it needs. But the Michelson-Gale experiment gets a full rotation when it uses the same apparatus, same principle. Everything's the same, except it's just turned around. The apparatus is turned around. Why is that?
Well, everything I've read about it seems to disprove ether and confirm relativity.
Well, whatever. I mean, explain it in your own words. Just make sense to us.
I've been trying to do that.
All right. So, how would relativity explain the Michelson-Gale experiment? If that's what your answer is.
Relativity, because
special relativity. How would that answer the Michelson-Gale experiment?
The Michelson-Gale experiment, well, the Michelson-Morley experiment would explain it, because, I mean, you can apply this either way. I mean, you're just kind of co-opting different explanations and saying, well, it could be this or it could be that.
No, I'm not. I'm saying, look, we have two experiments with two diametrically opposed results. The Michelson-Morley got barely any ether resistance at all. Michelson-Gale got a full ether resistance. One's measuring revolution, the other measuring rotation. Tell me, how do you explain that?
Well, one experiment with the lead blocks got no different results than one without. Or do it underground. Do it on the
But they
surface.
did get a different result, okay?
Did
The lead blocks aren't going to help you here. Michelson-Gale got a totally different result than Michelson-Morley. Explain why that's the case, if they both use the same apparatus.
Let me see here. Now you're saying. Let me talk about. This is really confusing me. That this ether thing. So ether particles can exist outside of atoms. Is that correct?
Outside of what? Atoms?
Atoms. Yeah.
Of course, yes.
Okay.
We've already been through that. Are you going to give me an answer to the Michelson-Gale and things experiment that I just presented to you or not?
I mean, I would have to read more on it. I honestly.
Okay. All right. That's an honest answer.
It's an honest answer. Sure.
All right. And what else do you want to know about ether?
I just don't understand the free ranging subatomic particle that's smaller than a gluon permeating densely through all of space. I don't understand that.
Well, best I can tell you is, I think I already said it, but I'll say it again, which is space can't be nothing, because nothing doesn't exist. It has to be something. The question is, how do we describe that something? Now, if that something is not the smallest particle, that means it's possible to have another particle that is the smallest. So what they do, they forget all that. You just said, let's go to the smallest possible particle that can exist without itself becoming energy or something else. It has to be matter. Okay? What is that? This is as far as we've come in quantum mechanics, called the Planck particle. That's as far as we come. Now, in 100 years from now, we may come further. Who knows? But the basic thing is, space cannot be nothing.
Well, nothing is a weird term, I think. But
yeah, I agree with you there. It is weird.
Yeah. Let me see. What do you think about exoplanets with gravitational microlensing? Like this relies on relativity working for
That's okay. I mean, there could be possible that light's bent and you're going to get the bending's going to create an illusion of another star there, possibly. I have no argument against that, but that has nothing to do with geocentricity versus heliocentricity.
Right. It's kind of the physics you're presenting for the whole model.
Well, I'm just using what Einstein gave us. This is the guy that said, I'm going to take back the ether and I'm going to have light travel through it. And if it does, it can increase or decrease in its speed. That's what he said. So that's our current science.
All right. Now, do you accept that the Apollo missions were real? We actually went to the moon? I mean, I don't know.
That's still on the shelf for me.
Okay. So if we did, which I believe we did, we would have to know where these things are in the universe. Like NASA either knows the sun is in the center or the Earth is in the center. How would they not know? How would they not know that? How would they not know that?
Because of relativity. You're the one who presented that first, right?
All right.
With your example of Jupiter.
Okay.
The math works for both of them. So they don't know where the sun is. It's all relative. That's why the other quote I should read from Einstein is a doozy, because if you don't mind me doing that here, he says, here it is. The struggle so violent in the early days of science between the views of Ptolemy and Copernicus would then be quite meaningless. Either coordinate system could be used with equal justification. The two sentences, the sun is at rest and the earth moves, or the sun moves and the earth is at rest, would simply mean two different conventions concerning two different coordinate systems.
Sure, that's kind of talking about like being on the earth and not knowing anything else. Like if you've been to the moon and you're looking outward from a different perspective, you would kind of have to know what is where and how it's moving.
Kind of have to.
I think you would have to, yes.
You couldn't tell if you were on the moon. If you
How?
were on Mars or Jupiter, because the stars are going to rotate every day, just like they do on Earth.
Sure.
You're going to have some other means to figure out whether you're in the center or they're in the center. But see, what we've done in this debate is shown that it's possible, you even said it yourself, for the Earth to be in the center, because of your Jupiter example, and not be moving. Okay? It's possible. Now, we have to go to the next step and find out, how do we figure this out?
Well, yeah, exactly. But the not be moving part, even if the Earth was in the center, it would be moving. Even exoplanets make the star wobble. That's how again, back to gravitational microlensing. It's looking at the stars wobble when these little planets are going around it. So even if the universe is going around the Earth is going to be moving, regardless of either.
Not necessarily. If there are other forces that keep the Earth in place, that's not going to be true.
What would those forces be?
The centrifugal, Coriolis, and Euler forces, the inertial forces created by the rotating universe.
And it would have to be completely even on all sides, basically, for that to work. Is what
Pretty
I'm
much,
saying.
yeah. Pretty much, yeah.
So the sun is over here. Some of the universe is over here. The sun's moving here. The universe is going around. So how is that possible with the sun's mass being on one side of the Earth at one point and another side at another point? And I'm not following the physics here.
Well, let's look at the tides.
Mm-hmm.
You understand the tides, right? We have 2 tides per day, right? Okay, so the water rises and then goes beneath, about 2 feet or so. So it's pretty significant.
Mm-hmm.
Now, if the Earth were moving, then we wouldn't have no tides, because in order for the water on the Earth to rise above the landmass has to stay still for the water to rise above it and then go down. Okay? So that's only going to happen on a fixed Earth. Because what happened? Tell me how that's not possible.
All right. Because the moon is orbiting the Earth. So
I understand that.
We don't have giant solar tides because of angular momentum. The Earth is moving around the sun.
Well, how is the moon and the sun not moving the landmass?
Because of angular momentum. The moon is moving around the Earth.
But how is it not moving? If it can move the water and the water's heavy, then why is it moving the landmass?
Why is it moving the landmass?
Why is it not?
Why is it not? It is. It's very slight, but it is moving the landmass.
It is.
By an inch or so, it'll rise up, but very slight. Is that
so? Is that a scientific fact?
It is.
It is? Okay. Well, you'll have to show that to me.
All right.
Okay.
Well, I can't demonstrate it at the current time, but I'll work on it.
Okay, do that. Maybe you can tell Donnie. Because my understanding is the landmass isn't moving, and that's why we have the tides, because the water is liquid.
Well, the landmass isn't moving like side to side so much that it's up.
Up? By how much?
Not very much, an inch or so, 2 inches. I'm not sure.
The landmass moves up and down an inch twice a day. Is that what you're saying?
That's correct.
Okay, I'd like to see proof of that.
I'm not sure. Yeah, okay. Something around that. I'm
Okay.
not sure exactly the amount.
All right, Donnie, where are we in our time and whatever?
We're actually at a few minutes of bonus minutes. We just hit the 90-minute mark. And so if you gentlemen feel like you've hit all the relevant points, this has been a fantastic back and forth discussion, very cordial. You both have given me an easy job tonight in terms of moderation. So did you want to jump into closing statements, or did you feel there was a final point or two you wanted to engage?
Yeah, let's do that. I'm okay with that. Jackson, are you?
Yeah, we can move the closing statements.
Yeah, and then we got just about 100 audience questions to get through. So get comfy, gentlemen. Get a pot of coffee.
If you guys want to skip the conclusion, I am open to that and get right to the questions.
That's fine. We can just go straight to questions.
Yeah. How about we do a 3-minute closing because I've been drinking a lot of water, and I'm going to take a real quick restroom break. That's about 3 minutes. So that'll be perfect. Jackson, let's start with you and then at least you guys can wrap up your thoughts and points and allow me to organize what I'm going to do to the audience. Since we have so many questions, I'm going to organize the most relevant and we'll go with those. Okay, Jackson, whenever you're ready, closing statement. Go ahead.
All right. Well, I don't have too much to say, but I'll try to be slow because Donnie's in the bathroom. But yeah, I mean, the debate will stand for itself. People will choose what side they want to believe. I mean, I think anyone who's watching this already has their mind made up and probably won't change their mind too readily. But having said that, I mean, keep your mind open to any possibility. I always try to do that. If the Earth is the center of the universe, I want to know that. But I don't think it is. And I thank Robert for doing this debate. He's been very cordial, and I hope I've been cordial too. I usually am. I try to be. So, I mean, I don't know if Donnie can click off me yet or not, but I'll just keep talking until he's back. Yeah, it was a fun debate. So I've been preparing for this for a while. I've watched a lot of Robert's material. I'm gonna have to look into the Michelson-Gale experiment a little more. I skimmed over that and didn't really have a good response for that. I will say that was my one major flub in this debate, I think. But I think we both did fairly well. Robert's an excellent debater. I've watched his debates before, so I'll give him that for sure. He's a good debater. But so this debate will, make up your mind who won, who lost, or was it a stalemate? It doesn't matter. Ultimately, it doesn't matter. Just look up your own information, do your own research, all that. So with that, I'll hand it over to Robert.
There we go. Okay. Jackson, that was one of your longest closing statements
yet. I was trying to be long.
You're setting new personal records. I forced you to have a longer one than usual. Yeah. Okay, Robert, go ahead. Take your time. 3 minutes, 5 minutes, whatever you need. Go ahead.
Okay, so I'll take some good time here because I want to introduce something else. I don't want to make a conclusion that when I saw this, it started me down the road, and I began to think very differently of scientists. Scientists accumulate a lot of data, telescopes, microscopes, oscilloscopes, you name it. They accumulate a lot of data. The question is, do they have the right interpretation that they put on the data? And I'll give you one good example of that, and that's Edwin Hubble. The Hubble Space Telescope is named after Edwin Hubble because he was one of the greatest astronomers we had in the 20th century. In 1929, he was looking at the galaxies through the new Mount Wilson telescope that was 100 centimeters wide. It was the biggest telescope in the world at that time. And for the first time in history, men saw galaxies. They were theorized as far back as Kant, who called them island universes, but he didn't see any because it didn't, just the telescopes weren't powerful enough. But now they were. So Hubble's seeing these galaxies, and day after day after day, he sees one peculiarity that is just really strange. The light coming from these galaxies, every single one of them outside of our local area, has a redshift. And that means that the starlight coming from the galaxy is shifted to the red end of the spectrum. We know what the spectrum is. We see rainbows all the time. Red on the top, blue on the bottom, and different colors in between. So it would be like you looking at a rainbow and seeing the red shifted down significantly enough that you can notice it. Okay, in the rainbow. So maybe the red, let's say the red part of the rainbow would be bigger, wider than the other colors. So much wider that you can see, wow, that's a different rainbow. Okay. Well, that's analogously what Hubble was seeing from the galaxies. The light was shifted to the red. Now he knew instinctively that if he's on Earth looking at these galaxies and all around him, northeast, southwest, northwest, whatever, every single galaxy has a redshift. What does that mean? Well, he says it in his book, 1937 book, the observational approach to cosmology, he says that means the Earth is in the center of the universe. Okay? Why? Well, because if we see redshift and we see no blue shifts, we see no green shifts, no yellow shifts, we just see red shifts, that means we got to be in the center. He said that, not me. Okay? And he says, now what's the scientist going to do with that information? He doesn't like it. You should see Hubble's language. He says, this is intolerable. This is a horrible thing. We can't accept this, that the Earth is in the center of the universe by seeing this redshift. What are we going to do about it? Well, here's what we do. We change the structure of the universe. We take out the center and we make it into a two-dimensional balloon. And we put all the galaxies on the surface of that balloon. And to make the redshift, what we have to do is blow the balloon. So we make the balloon expand. And that means that each galaxy on the surface of that balloon is going to get further and further away from every other galaxy. And what's that going to do to the light that's traveling between those galaxies? Voila! It's going to make it into a redshift. Okay? So that's how we get out of it. We switch from Euclidean geometry to two-dimensional Riemannian geometry. So that means we've just taken the center out. Okay? Now we just have two dimensions to deal with. We blow it up. We got redshift. There's our answer. And you know what that developed into? The Big Bang. Okay? Because the Big Bang starts real small, and then it goes into a balloon, and then it gets bigger and bigger and bigger, and all the galaxies are spreading apart, and that's how we can explain redshift. Okay? Now, I don't mind them doing that, but look, you did that. What was your motivation to do that? Your motivation was that you didn't want the Earth in the center of the universe. You said that was horrible. We can't live with that. Why? Well, because that means the church was right and Galileo was wrong. And that means all of science for the last 500 years was wrong, and we didn't even know it. Okay? And even Hawking, in his book that I quoted from, the Grand Illusion, he says the same thing in there. And he also says the same thing in his 1987 book. What was that called? I forget the title of it. Anyway, he says, you know, everything we see out there with redshift, it looks like the Earth is in the center of the universe. But there is another answer, he says. And that is that we have the balloon universe that Hubble gave us. We have all the galaxies on there, and they're all going away from one another. And that's why we see the redshift. And he says, now, which one do I prefer? Because both explanations fit. But which one do I prefer? Well, I prefer the one where all the galaxies are on the balloon and they're all expanding. And I don't like the one with the Earth in the center. And he says, you know why? He goes, because that would make us proud. And the one that puts us on the balloon where we're really nothing, we're not in the center, we're not special, well, that makes us humble. So he makes his scientific decision based on whether he wants to be humble or proud, not on the science, because the science won't answer the question for him. Because anybody can dream up any model they want to try to explain why the Earth can't be in the center of the universe, you see. Now, what does that tell us? It tells us that these scientists are motivated. They have an agenda to keep the Earth out of the center. Why? Well, I already explained why. Because if you put the Earth in the center, that means somebody put it there. And he's bigger and badder than you are. And someday he's going to be your judge. No man can live with that. So we'll use science to get God off the stage, and we'll get God off the stage by getting the Earth out of the center. Very simple. Okay? So that's my conclusion.
Okay, very good. Thank you so much, Dr. Robert Sungenis. And thank you to both our guests, Robert and Jackson, for an excellent debate tonight. Very professional, very cordial. And what I liked about it is there was a lot of questions asked, a lot of answers provided, and some solid back and forth discussion for people to enjoy and think about as they critically analyze this debate. So, okay, we're going to get right into our questions. How we typically do these, wherever the question's for. we'll just make sure they get the last word. Say the questions for you, Robert. You get to respond first. Jackson, feel free to provide a little input or feedback to it. And then we throw it back to Robert for the first or the last word. Okay, here we go. Excuse me. Question from Echoing Erudite. Question for Robert. If you're correct, how can the laws of physics be universal due to the laws of motion and gravity? Everything we do in space acts as if it would be here on Earth, or as it would here on Earth.
And it does, you see. But if you're the center of mass of the universe, that means the inertial forces are a lot lower here in the center than they would be at, say, the rim of the universe. Okay. We know the inertial forces are created by angular momentum. Okay. They're just going to be a lot higher than they would be here, but they're the same laws of physics. You get there the same way. Okay. So there's no difference in the laws of physics. It's just whether they're more or less depending on where you are in the universe.
Appreciate it, Robert. Jackson, if you had anything to add, go ahead.
Well, we're back to that center of mass thing, which just to me makes no sense at all. I mean, we're not the most massive object in the universe. How are we the center of mass? That's really the only comment I have. Okay,
well, the fallacy is that you're working on the premise that you have to have a large mass in order to be the center of mass. That's not what a center of mass is. The center of mass is actually the smallest point that it could be. Any object, whether large, small, or medium, is going to have a center of mass. So it's not dependent on the mass. It's dependent on where the center of mass is in any particular object.
Okay, very good, gentlemen. Next question comes in here from Born Again RN. Question for Robert. If geocentrism is true, why is our solar system on a spiral arm of the Milky Way galaxy? Wouldn't it be in its center? Wouldn't the Milky Way galaxy be revolving around it too?
Okay, so we don't know whether it's on a spiral arm. Let me just say that first. That's an assumption we make. Okay, the only galaxy we can see with our telescopes is the Andromeda galaxy, and it happens to be a spiral galaxy. So we just assume that the Milky Way is going to be a spiral galaxy also. So that's just number one, but that's not really the answer here. Let's say we are on one of the arms of the Milky Way. Okay, so what's going to happen is the Milky Way is going to revolve around the Earth just like all the other stars do, and the pinpoint is going to be the Earth around which it revolves. Because if the universe is moving, then it's going to carry the Milky Way galaxy with it. So the spiral arm of the Milky Way is going to be the pivot point around which the galaxy revolves. And we're going to see the same galaxy that you would see in the heliocentric system.
I appreciate it, Robert. Jackson, any thoughts?
We are in an arm of the galaxy. We can actually see two other arms beside our arm in this galaxy, even with amateur telescopes, a Sagittarius arm and another arm I can't think of the name of, but that's we're definitely in one of the arms of the galaxy.
All right, but that doesn't answer, that the fact that the whole galaxy can't revolve around the Earth.
Okay.
All right.
Awesome. Thank you, gentlemen. Okay. Kept pure in all ages. Question for Robert. What do you think of Simon Schack's Tychos model? Example, Earth's snail-paced motion as it orbits within the sun to Mars binary pair.
Well, you see, there have been models that have tried to answer the low degree of result they got in the Michelson-Morley experiment by saying, well, maybe the Earth is just moving a little bit. Okay, well, if you do that, then what you have to say, the Earth isn't revolving around the sun, that it is somewhere in the center, but it's moving away from the center or around the center at a 4 kilometer per second rate, because that's what they found in the average of all these interferometers. Okay, so that's one way to explain it. And actually, it came before Simon Schack. what the guy is named Crombet. He was a French astronomer. And he tried to answer the Michelson-Morley experiment by saying that the Earth is moving at the pace of a man walking. Okay, yeah, that's slower than 4 kilometers per second, but at least he tried to answer the Michelson-Morley experiment's low result. And that's what he came up with. I don't believe that, because I believe, as Einstein himself admitted, as Newton admitted, that the whole universe can revolve around the Earth. And if that's the case, then the universe is going to have its center of mass where the Earth is located. Otherwise, you're going to have all kinds of complications if the Earth doesn't occupy the center of mass of the universe. So I would deny that proposition by Simon Schach.
Thank you, Robert. Jackson, floor is yours.
I don't have too much to add to that one. We can go to the next question.
Okay, let's see here. Next question for the both of you. Jackson, you can start with this one this time if you'd like. Jopie.
Right.
Question from Jopie. Question for both. Can the sun and moon be holographic light focus effects in an electric universe?
I think the simple answer is probably not. And I mean, I don't think so. But yeah, that's
okay.
Simple
Robert,
answer.
what are your thoughts?
This comes from the flat Earth people. Okay, because what's his name? Sargent. I forget his first name. A big guru of the Flat Earth Society says that we're not looking at real stars and sun. It's all holographic. Okay. The reason he says that is because he can't explain a lot of things that need to be explained if you believe in a flat Earth. Like, for example, how is it that if you live on a flat Earth and you have a hemisphere of sky over you, how are you going to fit in the southern stars that are below the equator of the Earth into this hemisphere? Okay. Because the way we have it in the globe Earth is you have a northern hemisphere and a southern hemisphere, and each of them contains different stars, different constellations. Okay. So if you have just one hemisphere, how are you going to fit all the stars in there? And then, so he comes up with this theory. Well, they're all holograms anyway, so nothing to worry about.
Problem solved.
All right, we're in agreement there. So wrong side. We're in agreement.
Just figure out a way to shake hands. We have some agreement. Gentlemen, pound it if you want to. For those who are interested in the flat Earth topic, Dr. Sungenis was here maybe a month and a half ago for a flat Earth debate against Nathan Thompson, one of those, Nathan Erickson. And so that was an excellent debate. Do check that out. And okay, next question then comes in from I Am Rick. Question for Robert. If the sun is 93 million miles away, question from Rick Flair, it looks like. So very cool. What speed would it have to travel to orbit the Earth in 24 hours?
Oh, well, you just take I think it's 6 trillion miles it would have to travel. And you divide that by 24, that would be your speed.
Very good. Thanks, Robert. Jackson, floor is yours.
Well, Robert himself has said everything past Saturn would be moving faster than light. And like my calculations, if they're right, I'm not the best person to ask about math, but everything at 14 billion or 13 billion light years is traveling like 200,000 times the speed of light, at least. So I think it really doesn't work here.
All right. So it will work because it's not the planet that's moving or the sun that's moving. It's the universe that is rotating, and it carries everything within it. Okay. The things that are further away from Earth, the universe will carry faster because it's like a record player. The further you get from the spindle outward, the faster that record has to travel. Okay. But the whole thing is moving. Okay. So we're saying that the universe itself is rotating, and that's what's traveling faster than the speed of light, is the universe itself. And Einstein's general relativity allows that. And we have the equations to prove it.
Thank you, Robert. Jackson, anything you wanted to add?
Just that Robert seems to have a problem with the universe expanding faster than light, but rotating way faster than light. It's fine.
No, I don't have a problem. I'm just saying they have contradictions. If you're holding to special relativity and the speed of light is limited, well, then how are you going to jump from that to an expanding universe that's going faster than the speed of light? Well, this is what you do. You go to general relativity, you see? And that's what they've been doing for the last 100 years. If it doesn't work with special relativity, we'll jump to general relativity.
All right, very good, gentlemen. Next question comes in for you, Jackson. So now you're in the hot seat. Matt Tithyahu, question for Jackson. In the heliocentric model, the Earth travels around the sun 66,600 miles per hour. Where is the point in our atmosphere where a ship gets left behind?
I think what he's saying is, why don't things get blown off the Earth at this speed? Is that what he's saying? For the same reason, if you're holding a glass of water in a car going 60 miles per hour, the glass doesn't fly, the water doesn't fly out of your glass. I mean, I think that's what he's asking. That's pretty much the explanation for that.
Okay. Any thoughts from you, Robert?
Yeah, I would just say that it's another flat Earth question.
Mm-hmm.
The reason for that is they don't have gravity in their system. If you ask a flat earther where you get gravity from, they'll make up all kinds of things except the fact that it doesn't work like the gravity we have. They'll talk about atmospheric pressure and the fact that the flat Earth is expanding upward, and so that makes the inertial force go down, all kinds of things like that. But they don't understand that the gravity envelope of the Earth is strong enough to have, 32 feet per second that a rocket's going to have to travel, or accelerate, I should say, in order to escape Earth's gravity. That's pretty big. Okay, so that gravity envelope is going to hold that ship to the Earth. And I'm defending the heliocentric system here. Okay, so that I'm showing that everything's equalized. You know, we don't have an advantage with gravity in the geocentric system over the heliocentric, but that gravity is going to be strong enough to hold that ship to where it is. And so there's not going to be any inertial force that's going to make that ship move backwards with the Earth moving. And as a matter of fact, if the Earth is moving at a constant rate, even though it's accelerating because it's going in a circular motion, the fact is it's a uniform rate, relatively speaking. So it's not like going back and forth, you know. So that would cause inertial forces. And yes, the ship would be affected. But if it's going at a uniform rate, it's not going to affect the ship at all.
Okay, I appreciate it. Jackson, this one, see, we got some more agreements there. We got to get more flat Earth questions in it. One day we'll do a 2 versus 2 flat Earth debate. Robert and Jackson team up. Okay, so here, a question for Robert. And let's see the question here. It might be more of a statement. The principle of relativity applies to all planets, not just Earth. So your argument for geocentrism is biblical rather than physical, since the physics applies to every planet. Any thoughts on that, Robert?
Yeah, we've already talked about this. So he must not have seen the debate, because we agree that you could put Jupiter in the center and figure it out mathematically that everything would go around Jupiter. Okay. So what we have accomplished in this debate then is to say it's possible that the Earth is in the center and not moving, and scientific. Okay. The next question is, after we've resolved the resolution, what steps do we take to show that it's not Jupiter, that the Earth is in the center? Well, we've had all kinds of experiments. We've had the Arago experiments as what was that? 1810 was the first one. He found that the Earth wasn't moving when he could measure the starlight coming to Earth. You had the George Bedell Airy experiment in 1871, where he used 2 telescopes, one filled with water, one filled with air, to measure the starlight coming from one star. He found, they call it Airy's failure, because he couldn't prove that the Earth was moving. Okay. Then you had Michelson-Morley come along, 1881, 1887, 1897. He did it again. And then he found another partner. Morley and Miller did experiments in 1904 to 1908. And then Miller did them on his own from 1908 to 1928. And the last one you had was Joos, Joos, in 1930. So basically you had almost 100 years of experiments that showed, okay, so what planet is in the center? And it showed that the Earth was in the center. Now, granted, there are a lot of people that, oh, well, I don't agree with that, and here's the reason why, and blah, 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 blah. But they could show that at least we had evidence that it was the Earth that was in the center, because they couldn't measure the revolution of the Earth around the sun with their very sensitive interferometers. Okay? And then you have stuff like I put in my movie, where the microwave background radiation, the CMB, they call it. They've had 3 experiments now, 1990, 2001, and 2009. All 3 of them came back with the same evidence that showed that the microwave radiation is oriented around the ecliptic between the sun and the Earth, as opposed to any other part of the universe. Now, how can that be if we're not special? That somehow the Creator oriented everything that shows that this ancient microwave is centered around the Earth. Okay, so we have evidence. Now, granted, there's other people going to come along. Well, I can explain it this way or that way, but look, at least we have the evidence. There it is. Interpret it as you will, but it shows that the possibility that the Earth is there is pretty great.
Thank you, Robert. I appreciate that. Jackson, any thoughts at all?
Yeah, the thing about the cosmic microwave background, the anisotropy of the microwave background radiation, I think that could be explained by all the measurements seem to have been taken from the L2 Lagrange point around Earth. And with anisotropy, I think you need multiple angles of measurement. Like this is the thing in ultrasound. That's why they move the ultrasound probe around, because you get an anisotropic anomaly if you only measure one area. So if you put these probes around Mars and measure the cosmic microwave background from there, and you got the same result, maybe that would say something. But I think measuring it from one spot, the L2 Lagrange point, I think that may be an explanation. There may be some totally different explanation. The other thing, if again, Mars, if you did all these experiments that we do on Earth to try to prove the Earth is rotating or not, if you do it on Mars, you're going to get the same results, I think. So
you think, but you don't know. Okay.
Right.
I mean, you're asking me if I have scientific evidence now. I say, yeah, because it's been done on Earth. If you do it on Mars someday, yeah, you can use that as evidence, but you haven't. So you
right.
can't use
I'm saying if you do, I think it would.
Yeah. Well, see, what you think and I think doesn't matter.
Right.
That's why we're debating it.
Yeah.
Okay, very good, gentlemen. We're down to our last couple questions. Been a good Q&A. I'm really enjoying this. Okay, Stephen Tibbetts, question for Dr. sungenis. If the Earth is motionless, how can we use parallax angles to get stellar distances?
Yeah, I was wondering if that would come up. See, this is one of the impressions that people are under, that stellar parallax proved heliocentrism. No, it didn't. Okay, it took us a while to figure it out, but it's very simple. You're going to get the same angles if the sun goes around, or if the stars go around the Earth, as opposed to the Earth moving against fixed stars. Okay, I mean, it just makes common sense. All right. I try to illustrate this to people by saying, let's say you're in a carousel, okay, and you're in the middle of the carousel, and you're standing in one position, you're not going to move. the carousel is going to go around you. See all the horses going around you, right? Okay. Now, let's stop that picture and now change it to you're in the center again, and this time you are moving. You're going to turn yourself around at the same rate that the carousel is turning around you. And what are you going to see? You're going to see as if it's like the carousel's turning around, although you know you're turning around. Okay. You're going to see all the horses go by in your line of vision, same as when the carousel was going around when you were in a fixed position. Okay. That's called relativity, motion relativity. So the same thing would have to apply to parallax. You're going to get the same angles, whether it's the Earth that's moving from one side to the other or the stars that move from one side to the other. Same difference. Okay. And these are all illustrated in my book. And we have animations of them to show you in motion how that would all look on film. So it's all available. You can buy it in my flash drive, which is $39.95. And but it's all there. So you can see it for yourself.
Awesome. Thank you, Robert. Jackson, any thoughts?
I don't have too much to add to this one, really. I mean, yeah.
There you go, Robert.
So
you get the last word, Robert.
Last word? This is it? This is over? It's over?
Well, I guess the last word on that one, if you have anything to rebut.
No, I have
nothing. Okay. So.
Well, let me just add here that it's the same for stellar aberration. That was used by what's his name? I forget the guy, 1787. He is the first guy to say stellar aberration was going to prove heliocentrism, and it doesn't, because exactly by the same principle I just said about the relative nature of motion, you're going to see stellar aberration in the geocentric model. Okay, it just took them a while to figure that out, and the reason is because everybody was being pressured to believe in heliocentrism. There were no geocentrists out there. You know, there were a couple, but not many that could stem the tide and say, hey, did you ever think about the relative motion of this? And I can explain it to you on a film and you can see it for yourself. There wasn't that many out there. This just didn't happen until like the last, maybe what? Since Einstein, basically, you know? So that's what we're stuck with.
Thank you, Robert. Okay, we got two more questions. One for you, Jackson. This one's for you. We got one more for Robert. Then we're going to wrap it up. Appreciate the time you've both given to us. So this one comes in from L. Ram. Question for Jackson. We know the sun revolves around its own elliptical path. Therefore, it's moving. Do all stars remain stationary without exception, or do a number of them also revolve?
No, I've been talking about that this whole debate, that stars wobble because of planets and other things around them. They don't orbit other things always. Well, a binary star will orbit another star, but they'll wobble in their stationary position. So that's what I've been saying.
Okay, thank you, Jackson. Robert, any thoughts?
The sun revolves around its very own elliptical path. It's not an elliptical path. We would not call it an elliptical path. The sun would have, if it's rotating, it's going to have a slight precession. Okay, that means the axis of rotation is going to wobble, if you want to use that term, in a little circle over a period of years. It's going to do that. Okay, so that's the only motion that those stars would have, unless there's another star near it, and that's what we call binary stars. And 50% of the stars we see out there are binary stars. So yes, and that's it. The closer they are, the more they are going to revolve around one another. Okay, and they have to revolve at such a speed where they don't fall into each other. Okay, and that's an intriguing thing because they have to move pretty fast in order to avoid each other. There are stars that have what they call proper motion. Proper meaning that the star moves independently of the other stars that are out there. Okay, that's an anomaly. They can't explain it, but they know that these stars move because they see them in different places compared to the constellations they looked at the year prior. Okay, so There are stars that do that. There are stars that pulsate, like Betelgeuse. It gets really big, and then it gets small, and then it gets big. And we can tell this by the amount of light that it emanates. Okay, so there is movement around in the stars and in binary systems, but that movement is minimal when you get to constellations. They appear the same way now as they did thousands of years ago. So we don't see any great relative motion between the stars, like say in the Milky Way. They're all the same. So the only motion that the geocentrists would ascribe to the stars, however, is the fact that they're all rotating around the Earth daily because the universe is taking them all around the Earth daily. It's like a bowling ball. If you put a bowling ball on a table and you rotate the bowling ball, well, what's rotating? The bowling ball is rotating. That would represent the universe, but everything inside that bowling ball, whatever it's made of, it's all rotating the same, you see. And so that's how we would say the stars are moving.
Thank you, Robert. Jackson, question was for you. Did you want the final word?
Not too much. Just want to add an interesting fact. They think you mentioned Betelgeuse. They think Betelgeuse is like decades away from going supernova based on how it's acting. So just be watching the sky, I guess.
Could be any day.
Yeah.
Now, Betelgeuse, by the way, your viewers might want to know this, is the constellation Orion, the guy, the hunter, and you can tell because he's got the 3 stars as his belt, and you can see that practically anywhere because it's positioned almost perfectly in the sky. But Betelgeuse is the star that is on his left shoulder. On his left, so like if Orion is facing us, Betelgeuse is the star on his left shoulder, so you can see it real easy in the sky.
Very cool. Okay, well, we got the last question now, and it's for you, Robert, and then we're going to wrap things up. So question for Robert: do black holes revolve around the Earth?
Yes. Everything that's in the universe revolves around the Earth.
Okay, great. Jackson, anything you want to add?
I would say no, they do not. And that's basically our positions tonight. Yeah.
And that's why everybody needs to go back who just joined us and watch the debate from the beginning. It's been very informative, very comprehensive, and I think the kind of debate that people who are on the fence, regardless of whatever their view is on this issue, watch this debate critically and come to your own conclusion. Awesome Lawson Clips sends in a super chat. Appreciate the support. Okay, gentlemen, that wraps things up. I do really appreciate the professionalism tonight. It's been an excellent debate. Robert, Jackson, always great to have the both of you here for these debates. And so if you wanted some real quick final words, Jackson, why don't we start with you? Thanks again for doing this. It's been an excellent debate, and go ahead.
Yeah, it was a lot of fun. So I have to say, really, I'm exhausted after 2 hours of doing this, but yeah, it was fun. Thank you, Robert, for doing this. Thank you, Donnie, for hosting, and thank you to the audience. Like and subscribe.
All right, very good, Jackson. I appreciate it. Robert, always a pleasure and a privilege. Hope you enjoyed the debate, and again, thank you for your time. Final words, final thoughts.
Jackson, thank you for making it a good debate.
Yeah,
I mean, I've had some debate opponents that. What was the other guy, Donnie? I had to leave the debate. He was just so. What would you call that? I still think about him from time to time. Anyway, so anybody else who's interested in this topic, we have a lot of material available. You can go to the website journeytothecenteroftheuniverse.com, and you'll see everything we have. We have probably a dozen books. We've got half a dozen movies. And what else? We had a flash drive with all the animations on it. As I was saying, there are 60 animations on that flash drive that are invaluable in understanding this. That's it. So it's all available if you want it.
Very good. And to those in the audience, the description box of this video, check it out. All those relevant links that Dr. Sungenis is talking about are in the description box. So check that out and utilize the material there. Okay, so we are going to wrap it up to the audience. Thank you so much for tuning in. Excellent feedback. We've had well over 100 people the entire time enjoying this live. And so, okay, God bless all. Thanks again for tuning in. And Standing for Truth is out.
Okay.